So we know that elements have their own little rooms, orbitals, for their electrons. And we know that the protons and neutrons are in the nucleus. So everybody has their own little space. Why do these atoms, different types of elements, why do they even come together to form compounds? A compound is two or more atoms, whether it be one type of atom, right, or more than one type. Why do they come together? And the reason is, and it usually has to do with some sort of reason relating to energy. So atoms bond together because the compound is more stable and lower in energy. And they get there by achieving a noble gas configuration. Everybody wants to have a noble gas configuration. So what atoms will do is bond together and share electrons so that they each have that noble gas configuration. So carbons do this with each other and with hydrogen to form those covalent bonds and end up having each their own noble gas configuration. Here are some examples of molecules or compounds. Those are synonyms. Here are some examples of compounds that are sharing electrons. In other words, they have covalent bonds. We have different ways to represent these. So we have the electron dot structures where you actually are placing in the electrons and writing all electrons in and showing how they're shared between each element. So here you can see those green atom those green electrons are from the hydrogen, and the black ones are from carbon. And you can see the same thing with these other compounds. These are what we call Lewis structures. We can also, those are the most basic Lewis structures, but we can also represent Lewis structures using lines. And the way I like to think about it mentally to know that each line is two electrons is I like to think, okay, there's one electron at this end, there's another one at this end. Now, this is just for me to remember, okay, one line means two electrons. It's not because there's one electron always sticking next to hydrogen and the other one is always staying nearby the carbon. That's not how it works. Remember, electrons are always moving around in their little clouds, in their orbitals, and they're not staying still, right? It's not static. So again, these are Lewis structures also. They just happen to have a specific name. You can call them line bond structures or Kekulé structures. We have methane here, ammonia, water, and I believe this is methanol. My face is covering it up, but on your slides it should show the name. Now, if you need a refresher on drawing Lewis structures, I will link those videos, both my video of how to do that and also maybe some other resources. So there is a pattern that I would like for you to start recognizing. If you start getting this pattern down and memorizing it slash having it handy, right? You could just have this written on a sticky note or something and always have it with you with your notes. However it is that you keep important details, right? When you're studying, hydrogen will always form one bond because it only has one electron when it's neutral, and to fill that s orbital, that one little s orbital that it is occupying, that one electron, to fill that, you need one more electron. So what's it going to do? It's going to form one bond with whatever element it's bonding to share each electron coming from each one of those, and then it has a noble gas configuration. The same idea for the rest of these. Carbon has 4 valence electrons, meaning it has 4 outermost electrons, and elements in the second period and below, they typically want to have 8 electrons around them. We will mostly just encounter second period and third period elements. Not really, we won't dig into anything really bigger than that, but those elements, carbon, nitrogen, sulfur, oxygen, these like to have 8 electrons around them. So carbon, it has 4 electrons around it by itself, 4 valence electrons, so it's going to form 4 bonds to fill those other 4 that are missing. Again, same idea with nitrogen, same idea with oxygen. Nitrogen will form 3 bonds, oxygen will form 2 bonds. Sulfur, it's under oxygen, right? It's part of the same family. It will also form 2 bonds. And then all these halogens here, these are all in that group to the left of the noble gases. These are just missing 1 electron from becoming noble gas configuration. So they just need 1 bond, similar to hydrogen. But notice that these have more electrons around them because they actually have access to more orbitals. Hydrogen only has that 1 s orbital. So we know that lines represent bonds, and specifically each bond has 2 electrons. Now, what about these other dots that you're going to see? These other electrons, those are called non-bonding / lone pair. You will mostly hear me say lone pair. Those are called lone pair electrons. They are not bonded, but they're there and they should be represented. And this is typically the representation you will encounter. So how are these compounds actually shaped in 3D? Picking up on this and being able to visualize in your brain is actually going to be pretty important in this class. Now, I'm not saying you necessarily need to buy a molecular model kit, but it would be helpful. However, we do have many simulations that you can use that can serve that purpose. So, these representations of carbon compounds, we talked about the line structures and the electron dot structures. There are some other ways that you're going to see compounds represented in this class. You are going to see this representation a lot later on, specifically chapter 5. What does this representation mean? Just so that you kind of have a primer to this later on. The lines, those are normal, how you have typically encountered them. They're just bonds. Now, because they are not a different type of line, or this wedge right here, those are in the plane. And what we mean by in the plane is that is like, it is on this plane, right? It's like this, flat. So we have one hydrogen going up, another hydrogen going down. Now, we have a hydrogen that's a wedge, and we have a hydrogen that's dashed. The wedge line means that hydrogen is coming towards you. Sorry, that hydrogen is coming towards you. It's coming out of the plane towards the viewer. And the dashed line means it's coming to the back. So it's pointing towards me. The other hydrogen is pointing towards you in the camera. So I just want to give you that broad idea to kind of start digesting it by the time we get to chapter 5. Now, if you were to drape a blanket, a sheet over this little carbon compound, and I'm going to have molecular models to show you by the time we get to chapter 5. If we were to have this little compound and drape like a sheet over it or a towel or something, it's going to form this tetrahedron. And what this is it's sort of like a pyramid, and it has 4 faces. It has 1, 2, 3, right? 1, 2, and then the one in the back, 3, and then 1 at the bottom, and they're all triangle shaped. So like I mentioned, there are many simulations that we can use to visualize these compounds in 3D, and that's what we're going to do right now. We don't have to worry about what these compounds are called or anything like that. I just want to show you how they look in 3D and how you can use these simulations to turn them around, flip them, so you can kind of start getting an idea of these 3D structures, right? We're no longer talking about just flat in the plane on your paper compounds. So if you successfully loaded the simulation linked on our slides, you will see this website, MolView. Now, there's a lot of things you can do on here. You can sign up and sign in and save molecules on here and all of that, right? We can get to that later. What we want to do right now is just search for methane, because for you it might not have been already loaded. I had already searched it, that's why it's there. But if you don't have it, just search it up here in this bar. So now we have methane here. That's the compound we were just talking about in 3D, right? With the dashed wedge and with the dashed line and the wedge. Remember, the wedge means it's coming towards you and the dash means it's going to the back. And then there are always going to be two of the atoms connected to carbon in the plane. So what do we mean by this? So let's kind of turn it around real quick, just so I can first orient you to what we mean by the tetrahedron. So imagine, again, draping a cloth over this, a sheet, anything. It would hang and it would form a triangle here, a triangle on the other side, and then a triangle on that far side. And then at the bottom of the base, we would have another triangle. That's what we mean by tetrahedron, that we have four sides. Tetra is four, hedron means sides. So it's always going to be shaped like this little tripod. And notice that as it being a tripod, if we consider this screen our plane, one of our planes, these right here are in plane, right? Those are the regular line bonds. The other two bonds, remember, we're going to have one wedge coming towards you and one dash in the back. So this one right here is coming towards you. That other one back there is going to the back. So this is what I want you to start just, kind of percolating in your brain before we get to those later chapters. And you can, again, you can search up any compounds that you want here. They are most likely going to be here. Heptane, this is just a chain, and you can see that this chain of a bunch of carbons and hydrogens, the hydrogens are the ones on the end, also have that same structure, the tetrahedral structure. You have two bonds in the plane, and then you have one going to the back, one going to the front. So you can search up whatever you want and start getting a hang of those patterns.